Right. Yeah. Direct. Yeah.
Back then,
Okay. Let's get going today. We'll be talking mostly about models involving ordinal variables, whether that's the outcome or predictors. We're going to be using mostly the BRMS package for that, which is very strong in dealing with ordinal variables as more advanced stuff than what is available in RCR. So we want to learn how to do those things, understanding that because this is Columbia, Columbia is always trying to develop Stan and obtain more grants to do so, and the fact that I teach with Stan, use Stan outside of Columbia, seeking grants, whatever, creates appearance of a conflict of interest that you should be aware of, even though we're mostly, again, talking about BRMS. Which was, or I mean, it uses Stan, but it was created by someone who was in Germany, who was doing his PhD, rather than at Columbia. So here are some graphs that help to get some intuition for what is going on when we're estimating these ordinal models. And so this is for, you can just we'll talk more about how ordinal models are specified in a second, but you can just imagine that there's no predictors or anything. You're just trying to estimate the proportion of people who are in each category of some outcome variable that's ordinal. So these, in the social sciences, are often so-called Likert scales, where you might have like 5 categories of the outcome: strongly disagree, kind of disagree, neutral, kind of agree, strongly agree, something like that. It's a very common way to do surveys for various outcome variables. And the way that we think of this is that everyone sort of has a utility function or each survey respondent has a utility function for whatever the survey question is asking their opinion about, and they put themselves in the bucket that would give them the most utility if whatever hypothetical thing asked by the question were to transpire. And the way in which we model these things is having a CDF, in this case the standard normal CDF, although a lot of times we use the logistic instead of the normal, and having these cut points in the distribution such that, okay, if your utility for whatever is being talked about is like negative 1.4 or less, you're to the left of this vertical red line here, then you're going to answer in category 1. And if your utility is like close to -1, you're in this sort of narrow range here, then you're going to answer in category 2. And then if you're to the right, 3, 4, 5, anywhere to the right of like 0.5 on standard normal utility, then you're answering the highest of the 5 categories. And these same thresholds or cut points can be mapped onto the CDF, in this case of the standard normal. So these are all in the same place. And it's basically saying, okay, if you're between here and there in cumulative probability, then you're going to be answering in category 4, etc. And so that we want to be estimating those cut points. And so if we have no predictors, that difference between cut points on the CDF scale is just going to be the probability of you answering in any of the 5 categories. If we're talking about cutting through the PDF, then the area between thresholds is the probability of someone answering in those categories. But when we go to model these things, we're often going to have 1 or more predictors, and that can shift the individual person's utility or expectation of utility around in this distribution. So this now refers to the errors. And we can estimate the effects of coefficients. We can do nonlinear stuff, all kinds of things. But this idea of having cut points through a CDF is something that is sort of unique to the idea of modeling ordinal variables. You see the same thing if you estimate ordinal variable using frequentist methods such as maximum likelihood. They're also going to be estimating these cut points, but like with any frequentist method, it's not really giving you a posterior distribution of what you should believe about the coefficients or the other parameters conditional on the data. It's giving you these point estimates and sort of asymptotic distributions as to, what would happen if you applied this maximum likelihood estimator across many random samples from the same population. And we're asking these survey questions. So giving you a distribution of an estimator across data sets as opposed to giving you a distribution of beliefs conditional on the data and obviously whatever you believed about the coefficients before you saw the data. So we'll see how to do this in STAN and BRMS, but if there are any questions about the idea of an ordinal outcome or this idea of using these thresholds through the CDF in order to come up with the probability that you answer category 2, category 3, etc. Yes.
Is there no advantage in making the intervals equidistant?
Well, that is an assumption you could make, in which case you're only estimating one additional parameter instead of 4 in this case. But that's a pretty strong assumption to make, unless, so in some cases you will see and we'll see this a little bit later, the cut points are actually built into the survey question. So it's one of these things like, do you strongly disagree, kind of disagree, etc. It's sort of a strong assumption to restrict the cut points to be equally spaced. But in other cases, they'll ask like, how old are you? Between 20 and 30, between 30 and 40, etc. And so the people actually see what are the numerical boundaries. And in a situation like that, you could, sort of convert this to ratio scale units rather than merely these interval scale units that don't have like a well-defined 0. But moreover, like if they sort of give you 10 age buckets where you can put yourself in, then maybe it is more reasonable because people can really internalize that, 40 is the same amount away from 30 as it is from 50, etc. Which is not self-evidently true if we're talking about the difference between like agree and strongly agree. And particularly if we're talking about like doing survey research across different countries or in different languages. So how it is they like translate the difference between sort of agree and strongly agree can be like very different. Like even among people who like ostensibly speak English, like no one in Britain ever says they strongly agree with anything. Like the range is just like kind of disagree to agree. So yeah, you could make a rather strong assumption about equidistant, but it's probably better to allow them to be any distance apart and maybe put a prior that tends to enforce equidistance, but not mandate it, or prior that supports equidistant, but not required. Anyway, we'll see how that looks like before getting some more terminology. So we have K random variables that may be defined on a sample space if they're observable, or a parameter space if they're not observable, such that each of them, that should be xk there instead of just x1, such that each of them are non-negative and they add up to 1. Those variables are said to form a simplex. And so a simplex is basically a probability mass function, or it satisfies all the requirements for a probability mass function. But implicit in that, or really explicit in that, the constraint that all of the k x values add up to 1 implies that each of them are not independent of all the others of them. So because you have k random variables that add up to 1, if you knew any k minus 1 of them, you could exactly figure out the remaining one just by doing 1 minus the sum of the rest of them. So they're most definitely not independent of each other, and in situations like that, you need to definitely think of them jointly rather than merely marginally. So, you know, a lot of times with R, talking about regression coefficients or whatever, you can get away with saying your beliefs about each one of those are independent, even though, like, maybe that's not what you actually believe. But for these multivariate things, and we'll see some more of them as the weeks go on, we'll see more of them next week, where you have some multivariate inequality constraint, then there's no way to really fully understand that entity just from the margins. You have to be thinking about them jointly because of the dependence, the rather strong form of dependence that is part of the definition. And so simplexes are useful for a lot of things, one of which is that we'll see in the next couple of slides. The cumulative sum of a simplex is just an additive transformation of a simplex, and it's going to imply the last element of that cumulative sum is going to be exactly 1. But every element that's not the last one is going to be between 0 and 1, but they're going to be ordered. And so this is one way in which we can start thinking about how to think about variables that have random variables that have an order to them, is just by specifying the simplex and then taking a cumulative sum over it. Questions about the definition here? We'll see how to use it in a second. So if we have, you know, this type of variable, a simplex, what might be a prior distribution we could use for it? There are a few, but by far the most common and the most basic one that is applicable to a simplex is the Dirichlet distribution, which is basically a PDF over PMS. And the PDF, so here pi is going to be simplex, and it has some hyperparameters alpha that is just the product of each of the pi values raised to the power alpha minus 1. And then there's a normalizing constant out front, which is the multivariate beta function. It's basically the product of gamma functions divided by gamma function of the product. We've learned, or we've heard about the gamma function before. It's this integral that can be put in any more explicit form than this, but can be approximated extremely well numerically. Whether in R, that's going to be the gamma function. In Stan, it's the T gamma function. But of course, if we're doing this with Stan, we're going to be doing the logarithms of all these PDFs and whatever, in which case there's a logarithm of gamma function, which is denoted L gamma in both R and in Stan, but it's actually built in to the Dirichlet PDF. So under this distribution, the expectation for the marginal value of one of the components of the simplex is alpha divided by the sum of the alphas. So alpha would be something that you specify, you pass in as information, exogenous known. And the mode of the Dirichlet distribution is going to be alpha minus 1 divided by some of the alphas less 1, but Dirichlet only has a mode if the alpha values are greater than 1. And so it can be shown that basically Dirichlet is a multivariate generalization of the beta distribution. Indeed, each margin of Dirichlet is distributed beta. And so it inherits a lot of the same properties. And so we saw, well, you can have beta margins that are sort of U-shaped, in which case there's no unique mode. But when specifying priors, that's sort of a weird thing to think, that it's like either very close to 0 or very close to 1, but unlikely to be in the middle. So more common to either use uniform, which is a special case of the beta where all the most shape parameters are the same, or to have this upside down shaped U PDF that's going to have a mode and a mean and a median, etc. So you can also see, obviously, from this definition of the PDF that if the alpha values are equal to 1 for all k, then it's just going to be something raised to the power of 0, which is just this constant 1. And so the Dirichlet PDF is going to be have a constant density for every thing that satisfies the requirements of a simplex. And so that's essentially uniform distribution over that space. Consequently, setting all of them equal to 1 is a pretty common thing. Also, even if you're not going to set them all to 1, just to use the same alpha value for all k dimensions, it's also reasonably common, in which case alpha is known as a concentration hyperparameter. But if they're different values for different dimensions, then you can't really interpret it exactly as a concentration parameter. More generally, it's this sort of shape parameter that's kind of hard to think about. So it is definitely common to see people just use the same scalar value of alpha for all k dimensions, and in particular to use 1. So since Dirichlet distribution is a generalization of the beta, it's not surprising at all that it's conjugate prior for a multinomial likelihood, in much the same way when there's only k equal 2, the beta distribution is conjugate with a binomial likelihood. And so you can do conjugacy stuff in very simple situations, but if you start to do something more complicated, like put a hierarchical structure on the alphas or any of the things that we're going to do today, then you pretty much have to do stand rather than being able to do analytical calculations to get the whole posterior distribution. Anyway, we'll be using this as a prior on various parameters today. So if there's any questions about this, go ahead, ask them. So here again, I've put up sort of the contrast between a data generating process, a prior predictive distribution for an ordinal model with what you might think of as a logistic link function. And then in the right in blue, seeing how you would define a kernel function if you wanted to condition on ordinal outcomes that you've observed. So starting with the thing on the left, a function to draw from the prior predictive distribution. So this is going to return a matrix that has S rows and columns, and each one of those is going to be, each cell is going to have an integer saying what we predict a person with this or that X value, what their outcome would be if the outcome is measured in a ordinal basis. So we need to take in an integer for the number of simulations, an integer j for the number of categories that the outcome is measured in. So j would be an exogenous known, or it should be an exogenous known if you're the person doing the survey, or even if you're the person reading the documentation of the survey, that should be something that is fixed. We're going to have a concentration parameter A that's going to go into a Dirichlet prior. We have a location and scale that's going to go into a normal prior on the coefficient. And we have some continuous X variable that we're going to be predicting with. And obviously, we can do this with more than one X predictor. So we just figure out how many observations we're going to have from the size of X. And then we make a matrix to hold our prior predicted distributions that's going to be pulled out at the end. Not sure if I've used the rep vector function before, but it acts like rep in R. So here I'm taking in a scalar value for the concentration parameter on my Dirichlet prior, and I want to copy that J times to use when I specify the draws from the random generator when we get into them. So we're going to loop from S equal 1 to capital S, doing a bunch of draws from this prior predictive distribution and doing a bunch of draws for each observed value of X that we have. And the thing that's different here, and it kind of had to be crammed together because there was like not enough room on the slide for all of this, is this process of making the cut points under the prior. So we read this from inside out. We're going to be drawing from a Dirichlet distribution with shape parameters A repeated J times. Okay, so that's going to be a draw from the simplex. Going to be non-negative, add to 1. We're going to do the cumulative sum of that. And so now we have numbers that are between 0 and 1, except the last one is exactly 1. And to put this in the form of cut points for an ordered logit model, we're then going to apply the inverse CDF transformation of a logistic distribution, which is coded in Stan as logit. And so if we back up to this, what I'm basically saying, okay, look on the CDF, this one is standard normal, but it's basically the same idea for standard logistic. What I get when I draw from a Dirichlet is the increments on the vertical axis. And then when I cumulative sum them together, I get the points in which they are on the vertical axis. So like 0.1, 0.2, 0.4, 0.7, something like that. And now I'm applying the inverse CDF transformation, starting with these points on the vertical axis, going over to the curve, and then down to the horizontal axis. And where they land on the horizontal axis is going to be my realization of the cut points. And then once I have those cut points, I can go and fill the rest of the code for drawing from the prior predicted distribution. But this is sort of a idea that may be kind of unfamiliar if you haven't worked that much with these models before, and particularly if you haven't worked with these models in Stan, of, well, we can obtain realizations of draws along the horizontal axis by taking a draw of simplex, which gives us the increments, doing a cumulative sum, which gives us where the increments add up to on the vertical axis, over the curve down to get the cut points in utility space, basically, for putting people in the buckets. And so let's see the rest of this, and then maybe we can come back, ask some questions. So that's our realization of the cut points. For the Eseth simulation, we take a realization from the normal distribution to be our coefficient, and then we go, for each observation, we construct utility by multiplying our coefficient by the predictor and adding a random error from a standard logistic distribution. And so that is our model of the utility. And then we just have like a while loop here, and it got all mushed together, but a while loop where if we start y at 1, and if the utility is greater than the first cut point, then we bump up y. If it's greater than the second cut point, we bump it up again. But if it's less than one of the cut points, then we stop and we say, okay, this is our prior predicted value of y for that person, and we stick it into our matrix in the sth row and the nth column. When we're done with both of those loops, then we return the draws of prior predicted distributions at the end. So essentially what we're doing here, okay, we've talked about the process by which we get realizations of cut points. The horizontal axis here is utility space. And so for each person, we want to get a prior predicted value of their utility. Okay, we get a draw of beta from a normal prior distribution, use that beta to multiply by their x. That gives us basically the linear predictor of utility. We add on an error term that comes from a standard logistic distribution. Add that on, we get each person's utility for whatever this question is about, and then we see where their utility falls in relation to these cut points. And so if someone's utility is like 0.5 or whatever, we check whether it's greater than the first cut point. Yes, keep going. Check whether it's greater than the second cut point. Yes, keep going. Check whether it's greater than the third cut point. No. So in this case, we would stop saying the person is in the third category. So not in the first, not in the second, but yes, in the third. And so that is our prediction for the ordinal response for someone who has this X predictor. And we can do that irrespective of what utility they have. It's always going to fall in between some of these cut points, or in the extreme cases of 1 or 5. So does that help explain the prior predictive distribution for a model like this, which is really what we believe the data generating process to be before we see the data on the outcomes? So beta can be sort of difficult to interpret in models like these because utility doesn't have any units that are well defined. It's just basically relative to the standard deviation of the errors. Another thing that you might notice here is I could multiply u by any positive number and multiply beta by that number and multiply and change the standard deviation to that number. And I would get utility that is like bigger. But if I multiplied all the cut points by the same number, I get the same predictions for the outcomes. And that's why we fix the standard deviation of the errors to be 1 rather than something that we estimated in order to preclude that sort of multiplicative scaling. But that basically means that the units of utility are in terms of standard logistic errors, which is not something that a lot of people are going to find super intuitive. We can always get around that when we do the posterior distribution, because we can talk about predictions of observables, but basically a lot of people don't really interpret the coefficient that much except to say, is it positive or negative? Is there an increasing relationship between utility and this X predictor, or a decreasing relationship, or one that is not overtly positive or negative, but could be either positive or negative with reasonable amounts of probability. So when we go to estimate a posterior distribution, we're going to need, or someone's going to need to define a kernel of the posterior distribution in log units. So that is going to be a function of the parameters, the coefficient beta, and what I call the shares, which are the thing that is distributed Dirichlet in this model before we cumulative sum it and transform it and all this stuff. We're going to take in x We now have observed values of y, which we're going to put in a one-dimensional integer array, and then the hyperparameters we had before, which we're going to need to use to specify our priors. So we just pull out the number of observations from the number of rows of x, the number of categories there are in the outcome for whatever is the highest observed, when these are coded as integers. But I should have said this probably earlier, just because these are represented in Stan as integers, and they're represented in R and a lot of other software as integers, at least internally. So when you declare a factor in R, that's basically an integer vector with labels on it. But if you look at the labels, it's more clear that these variables don't have any actually ratio scale or interval scale properties. They're merely something that has a well-defined order to it. But anyway, they're coded in the Stan language as integers, but you shouldn't really do math on any of them. In any event, the last the maximum category is going to be the number of possible things that y could be. So we do what we did before, expanding out our concentration parameter to a vector of shape parameters that go into our Dirichlet prior. So our prior kernel is going to be the sum of a normal log PDF for the coefficient, given our prior location and scale, plus the logarithm of the Dirichlet PDF for these proportions or shares, given our vector of shape hyperparameters. So that accounts for our prior. We do a similar sort of thing to make the cut points. So we have the shares, we cumulative sum, and then we apply the logit transformation to use the inverse CDF of the logistic distribution. There's a bit of a quirk here, and that the ordered logistic LPMF in Stan, which we use for the log likelihood, takes a vector of j minus 1 cut points. Because as you can see, when you cumulative sum of the shares, if you did it all the way to j, the last value would be 1, and then the inverse CDF of 1 is going to take it to infinity. So implicitly, utility is always less than infinity, and so you don't need to pass in that to the ordered logistic LPMF likelihood. So we only do it for the first j minus 1 here, but the log likelihood function, like a lot of things, is already built in Stan, and sort the LPMF, because y is measured with integers or categorized with integers, given the linear predictor and the cut points is represented by ordered logistic LPMF. That gives us the log likelihood, and then the kernel in log units is just the sum of the prior in log units and the log likelihood. So if we had data on y that we collected, that we believe to have been generated on the process on the left in black, by defining this kernel function and giving this to Stan, Stan can draw from the posterior distribution of beta, which is our exogenous unknown, shares, which is our other exogenous unknown, and then the cut points would be, in this way of doing it, an example of an endogenous unknown. We don't know what they are, but we would know what they are if we do the shares. And so shares is the primitive, the exogenous unknown in this parameterization, and cut points is a deterministic function of an exogenous unknown. So that is would be considered an endogenous unknown in the sort of scheme that we've been using before, with the 4 categories of variables that could appear upon. So anyway, if you have outcome data that's ordinal that you believe to have been generated by the process on the left, you can use the function in blue, give it to Stan, as well as the data and whatnot. This is what BRMS and Ordinal are doing. And it can condition on the data to give you updated posterior distribution of beliefs about not only the exogenous unknowns, but the endogenous unknowns as well. Questions about that? So the likelihood for one of these ordinal models is for one observation, or the likelihood contribution of each observation to the likelihood of data and the cut points, which here I've represented as data, is just going to be categorical. And so really the only thing that's kind of tricky about these sorts of things is, how to set up what's the probability that Y is in the ith category or Y is in the jth category for the ith person or whatever. Like with Bernoulli models and binomial models, if the CDF you're using is in the location scale family, then you can basically use any of those. They're slightly different models, but the thing would be about the same. So here I've used the logit distribution for the errors. Consequently, I'm using the inverse CDF to map shares into cut points, etc. But if I wanted to use standard normal errors for the utility, then this would just be the transformation you need to do here is just the inverse CDF of the standard normal distribution. And now you have an ordered probit model. Or if these were, Cauchy errors, then now you have what's known as a quotient model. It's not used very much, but with any sort of CDF in the location scale family, you can use that as your inverse link function, basically, in an ordinal model. Now, it's not exactly an inverse link function the way frequentists would define it, because the ordinal model is not, technically speaking, generalized linear model if you were estimated by a maximum likelihood. But if you're doing one of these things in a Bayesian approach, particularly if you're doing it in Stan, it's basically the same process as any other GLM. And so from a Bayesian perspective, it kind of gets lumped together with Poisson and Bernoulli models and other things for other sorts of outcome variables that may be measured differently. So we can estimate an ordered logit model using RStanArm, and particularly the stan underscore POLR function, which is taken its syntax from the POLR function and the mass package, which estimates these sorts of models using maximum likelihood. Here have an example from a data set on how well inhalers were rated, depending on some treatment variable for people who have some sort of breathing condition. And so we can estimate that. Method equal probit is going to estimate ordered probit model. If method equal logit is actually the default, in which case it's going to be estimating a ordered logit model. Like stan LM, the stan underscore polar takes its prior on R squared rather than on the coefficients directly. However, in this case, it's a bit more difficult to specify conclusively what you think the R squared is going to be, because it refers to what proportion of the variation in utility you think can be explained by the predictors in your model. And as a general rule, our ability to explain unobservable things like utility is a lot less than our ability to explain observables like wages or log wages, something like that. So when in doubt, go small for the R squared, but obviously condition on the data, you can get updated beliefs about that and everything else. So anyway, rating is a ordered variable, and there's a treatment and whatnot, so we get the posterior distribution of that. We can estimate the treatment effect in terms of the latent utility units by creating a new data set, setting treatment to 1, obtaining our predictions, changing the treatment to be 0 for everybody, obtaining the predictions, and just taking the difference between those two things and summarizing them either numerically or graphically. In this case, it does seem to have a relatively precise effect that would tend to be negative. But again, these are in units that, what does negative 0.5 mean on utility scale? Not super interpretable, so you would want to try to, do posterior predict and other things like that you can put in observable of y. Unfortunately, Don Rubin and somebody else a few years ago proved that there's basically no good estimator of an average treatment effect in an ordinal model. Like the thing that you can do difference in means on has weird units, and everything else you can't do a difference in means on in a mathematically justified way. You can talk about medians, other things like that, but sort of the usual way of doing causal inferences in terms of average treatment effects doesn't really work well when the outcome is measured in an ordinal fashion. Anyway, so we get some results from our arm. Here are the posterior median and posterior standard deviation estimates for the coefficients up top, and for the cut points bottom. By default, there's this uniform Dirichlet on the shares prior, and then the cut points are an endogenous unknown, but anyway, they come out in the posterior distribution all the same, and so the posterior median of the cut point between the first category and the second category estimated to be 0.33, etc. And these medians, indeed the whole posterior distribution, is going to have an increasing order to it on these cut point thresholds between the categories. So questions about this means? Again, these coefficients and even the cut points are sort of with reference to this latent scale. And so, yeah, you can see, well, this is negative, pretty precisely estimated, unambiguously negative, but in terms of what that means for the observables, it's not exactly apparent from this, but I could get posterior predictions of the observables and then talk about, how many more people would answer in like better categories or whatnot if they had been the treatment group rather than the control group, things of that nature. Questions about this output here? Okay, so you can do relatively simple ordinal models in RCNR using R-squared priors. You can do more advanced, well, you can do the also simple, but also more advanced models for ordinal outcomes using the BRM function in the BRMS package. However, it does not have priors on R-squared, it just has priors on the coefficients, and in this case, also the cut points and whatnot. So we could use pretty much the same syntax, except family equal cumulative is what we need to do in order to specify the likelihood that corresponds to the likelihood we used before, except this by default is going to do ordered logistic, whereas we did ordered probit in the example before. But you could get that by specifying the link function. So that's the first version here, fit3. Estimate another model, which so all these coefficients, both in this and in the ARM example, are assumed to have the same coefficient across all categories. That assumption can be relaxed in BRMS by wrapping the one that you want to have category-specific effects in the CS function, and now it's going to estimate a different coefficient on that treatment variable for each of the categories of the outcome if you don't want to enforce that homogeneous effects structure. Also, you can use different families. So this is S ratio. It's a different type of ordinal model, a different sort of likelihood than this sort of proportional odds one that we did before. If we're talking about logit, there's a few different likelihood functions for ordinal outcomes that you can read about in the BRMS documentation that make somewhat different assumptions about the data generating process, but they all apply to ordinal variables. So we can estimate both of those. We can make calls to set prior, to put a weakly informative prior on the treatment effects and things like that. We can compare these two models as far as their expected log predicted density for future data, and we find out that we're basically indifferent between the two, which happens a lot. And so you could present both of them. You could get Lu model weights in order to obtain predictions to combine, or weights to combine the predictions with in an optimal fashion, etc. But there's sort of no strong evidence to prefer one form of the model to another with these data. And that kind of happens a lot because ordinal data don't have as much information in them as genuinely continuous do. So you have to have larger number of observations in order to get sort of equivalent amount of precision in the posterior distribution, assuming you're using like the same priors in both cases. This one doesn't have that many observations, and so we can't update our beliefs all that much. But given the observations that we have, we're updating our beliefs the appropriate amount. So just looking at what the results look like when you do this in BRM. So the first three things here are called intercept, 1, 2, and 3, which is those are cut points. They're just not labeled cut points. I think this is kind of misleading to call them intercepts. They're not sort of the conditional expectation of utility, given that someone's x values are all 0. But anyway, just when you see intercept in a cumulative model estimated by BRM, just mentally translate it into cut points. And so these are the logistic scales, so they're not going to be directly comparable to the ones that we got before, assuming normal errors, but again, they are constrained to be increasing under the default priors that we use when we get something like this. And then we get an estimate of the treatment effect, etc. In the next one, there was estimated with category-specific treatment effects. So one treatment effect for each level of the outcome. So we have the stuff that we saw before, but now we see different treatment effect estimates for different categories of the outcome. So the first two are reasonably precisely estimated, and we're fairly sure, at least 0.95 probability, that they're negative. However, for the third outcome category, the treatment effect has a posterior mean of 0.57, but a very large posterior standard deviation. It's about double that, and thus there's like a 50% chance that the treatment effect is negative and about a 50% chance the treatment effect is positive for the third treatment category. And the reason why this is the case is there weren't that many people who landed in the third category. So there's not a whole lot of information with which to update our posterior beliefs about that treatment effect for people in the third category, and that's sort of a consequence of us using independent priors, which may not be the best idea, but it's what we did for this model. So you might think that, okay, well, if the treatment effect is negative for the first two categories of the outcome, then it's more likely to be negative for the third category as well. But that sort of belief is not being reflected in the priors that we used in this particular case, although we could. Questions about that? Yeah.
So, monotonicity, I don't see it in the model here because the intercepts are not monotonically. When you have these category-specific effects, you need to combine them together in order to get the monotonicity thing to it. So that's why these are kind of called intercepts, is they're sort of interchangeable with category-specific dummy variables, and so it has to estimate them that way. But you'll find if you make the linear predictors and whatnot, there is an ordered relationship to the probability of falling in the lowest category versus the highest one. But again, with these sort of latent scales, it's sort of hard to interpret the numbers of these things. But when you do, you have to combine the category-specific dummy variables with the category-specific couples. Anyway, so kind of one of the issues with this is we might want to enforce some more structure on how the treatment effects vary across categories of the outcome. Or more generally speaking, if we have an ordered predictor, irrespective of whether the outcome variable is ordered or continuous or count or Bernoulli, whatever, oftentimes with ordered predictors, not always, but often, it's reasonable to assume that the coefficients on the respective dummy variables that are derived from an ordered factor are exhibiting a monotonic relationship, or that's our beliefs about them. So there's certainly exceptions to this. Age is definitely one that if you're talking about like some sort of growth or development, obviously babies are small, then people get bigger, and at some point you start to get smaller. So that is one that is like inconsistent with there being a monotonic relationship. But with a lot of other things, level of education, income, experience, these sorts of things, it is at least debatable. You should probably estimate a model that restricts those dummy variables to have an increasing or decreasing relationship when used as predictors, in some sort of a regression model. This can be done in STAN. It is done in BRMS. It can't really, or it isn't supported in RSTAN-ARM, but you can do it in BRMS when you wrap a ordered factor, when you put it in the formula, in an MO function for monotonic effect that will do this. And the way in which it does it is by scaling the cumulative sum of a simplex. And so the sort of base level, we have simplex, okay, values between 0 and 1 that sum to 1. Cumulative sum now makes this between 0 and 1 but ordered, and then multiplied by some scaled value, which can either be positive or negative on those things. And now the resulting coefficients are going to have a trend to them, positive if that scaling variable is positive, negative if that scaling variable is negative. And that probably would have been a better idea for these treatment effects that we estimated. But anyway, we'll show how to do one example next. There's more in the reading and there's more in the vignette for these monotonic effects in the BRMS package. So we're going to use the data set that we've seen before on preferences for president in the 2012 election between Obama and Mitt Romney. So we get this data, it's on Canvas. Again, it's coded, the 1 to win is 1 for Romney and 0 for Obama. So we run it through dplyr to get the basically data in the structure we need to use a binomial likelihood. All of these variables are categorical, but age and income are certainly categorical variables that have a natural ordering to them. And so when we go to specify this in BRM, we use this vertical bar thing that I referred to on Tuesday to then, okay, this is the count of the number of people in each dplyr stratum who favor Romney, and then the total number of people is the number of people who favor Romney plus number of people who favor Obama, and that syntax is what's used in BRMS when estimating models for a binomial likelihood. And then we're just going to put in region and gender and urban density as just regular variables, even though certainly we could be more specific about that based on historical understanding of how people voted in the United States. So like the South, certainly going to be more favorable toward the Republican candidate than other regions. Women are more likely to favor Democratic candidates than men are, etc. So we could put informative priors on those sorts of things. Urban density is another one that, rural areas are more likely to favor the Republican in most states. But what I wanted to show was how we can use the MO function to put a monotonic effect on age and income, both of which probably well justified by other literature. Older people more likely to favor the Republican, people with more wealth, which is sort of what income is proxying for here, more likely to favor Mitt Romney, well, former chief or whatever of Bain Capital. Anyway, so we put in the data set in the family binomial, and we get out this stuff. So, we have dummy variables for the regions, and, men are more likely to favor Romney than women, these sorts of things. Mo age and mo income are these scale factors that got multiplied by the cumulative simplex. And so you can interpret those as sort of the change in utility from going to the lowest category all the way to the highest category. So that is pretty conventional. We also get out these pieces of simplexes that were used in that monotonic effects deal. And so you can see these, well, they're rounded to 2 digits, but even if they were in like their full precision, 0.34, 0.31, 0.21, 0.09, and 0.05 add up to exactly 1. And then what they did to enforce this monotonic effect was to do the cumulative sum of these and then multiply it by mo age to get the coefficients on each of the age dummy variable categories. And the same thing with income. All these pieces here, they add up to 1. And then they were cumulative summed. And so now they have order to them. And then they got multiplied by 0.06, which is actually a lot closer to 0 than we probably would have thought in the scale factor here. And so that was not very precisely estimated with these data, even though there were a lot of observations in this data. So more of a strong effect of age than there was on income, which might be kind of surprising. But anyway, that's what you believe if, you know, those were your beliefs coming in, and then conditional on these data, which were taken from a poll like the day before the election. Questions about what this output is telling us, or the idea of having ordered monotonic effects of coefficients that are all on the dummy variables that are derived from the same ordered factor. So there was nothing in this, and indeed there probably shouldn't be, of saying like the order of the income coefficients is like bigger than the age coefficient. This monotonic effects things are just for that particular factor rather than like combined. But questions? So we saw a little bit with our stin arm that we can estimate effects that are smooth, but not necessarily linear, not necessarily monotonic. And we can do that with a variety of different sorts of outcomes using the stan_gam4 function in our stin arm. You can do much the same things, maybe even a little bit more with the BRM function. You can certainly estimate models for lots of different types of outcomes, having various nonlinear relationships to them. So there's a whole vignette about those. So one possibility is to estimate a nonlinear but structured form. So here we have some simulated data where there's an exponential relationship between the conditional mean of this outcome and whatever x is, scaled up by this b2. So we can have a prior specifying the NL par argument to indicate these are nonlinear parameters that we are referring to. When sometimes when you estimate some of these more complicated formulas, you have to wrap them in the BF function, which is not base factor, but like BRMS formula, to basically do a formula that has this sort of structure to it. Rather than being additive, it's multiplicative and, you know, exponential. Now, if you were going to do something like this in our stan arm, you could take like the logarithm of both sides. Or you could use a anti-log inverse link and sort of estimate the log of the intercept and the log of the coefficient here, and then make predictions and anti-log them at the end in order to get predictions in the units of the actual outcome variable y. You could certainly do that in BRMS as well, but with BRM, it can basically take this piece and stick it directly into the stan program to estimate these structured but nonlinear relationships between predictors and conditional means. And it just runs like, you know, anything else. Do want to specify informative priors usually for any sort of model like this in order to provide some regularization, but you get back estimates of B1 and B2 that have this posterior distribution along with estimated standard deviation of the errors in a normal model. You can do posterior Lindred, posterior predict, on things like that. So definitely you should not feel restricted to linear models, generalized linear models when doing Bayesian regression stuff. In terms of specifying the formula, it's basically as easy to do nonlinear stuff as it is to do linear stuff. Or it's as easy to do monotonic stuff as it is to do not monotonic stuff. And all these things, the reason why you don't see them in sort of historical software is because they either make it very hard to find the optimum, make it so we can't derive the sampling distribution of the estimator across data sets. Even if we can, you know, the number of observations that you need in order for these asymptotic results that somebody derived to reasonably hold is like, you know, way too high for the sorts of data sets that we're likely to collect in the social sciences, or 4 makes the coefficients difficult to interpret. And so if we just don't optimize, rather draw from the posterior distribution, we sort of instantly solve all the difficulties that you can get when you use optimization as your estimator by, you know, not caring about the distribution of anything across data sets, only caring about what we believe about the parameters conditional on the data we've actually observed. Then we don't have to worry about null distributions or any of that stuff, asymptotic relationships. And by, you know, doing our interpretations and our predictions in terms of counterfactual predictions on observables, then, you know, we can exhibit these nonlinear relationships that we think may be evident in the data. And if we go too crazy with the nonlinear stuff, estimate a model that's too complicated, overfits these data, unlikely to predict future data well, then Lou ought to tell us that in, you know, one form or another, so we could compare this with simpler models for this. But in this case, it's simulated data. We can see that this is the correct form for the data that we simulated. But obviously, we wouldn't know that if we sort of were conditioning on wild data. BRMS package has this really useful function called marginal effects, which allows you to plot the nonlinear relationships that you've embedded in your model, whether it's like this one, which was structured, or doing some like MGCV stuff to estimate a spline, anything like that. You can get a ggplot thing out. It'll show you the posterior median in dark blue there. It'll show you the 90%, I think, credible interval around that median with the gray ribbon. So you get uncertainty estimates anywhere along here, even though in this case, there's not that much uncertainty around the exponential relationship that we use to simulate the data and use to estimate the intercept and slope of. Because it's a ggplot object, you can re-theme it and recolor it and put the key and all sorts of other stuff just by using ggplot2 syntax. With that, in general, you know, the sorts of stuff you can do with the plots that come out of BRMS, very similar to the plots for base plot or RSNR. It's all basically the same stuff. But the marginal effects thing that Paul has done in BRMS is really good, works really well for a wide variety of models that are nonlinear between the relationship of the outcome and the predictors. So that's a good thing to always be calling to visualize. And you can even do it in like ordinal models or monotonic effect things. They have like a plot that's customized for each of those. Finally, we have an example from insurance. So here's another complicated-ish nonlinear model based on some data from an insurance company. So these data, like a lot of data, if they just sort of are dumped out of some database, it's sort of the dollar loss that the insurance company had for each of the people who bought insurance through them. So it was in like dollars. So one, that can be highly skewed, but two, like individual dollars are not really the right units of analysis. So I've divided it by 1,000 in order to get more reasonable units for the parameters. So this is sort of, you know, when you do one of these things and get the predictions, you know, if there was an expected difference of like 1 or whatever, that would correspond to an expected difference of 1,000 in actual dollars. But by putting things in more sensible units, it's easier for Stan to draw from that posterior distribution. So here we're saying the cumulative loss is some scale factor that's in the data, ULT, that I can't remember what any of these stand for, but anyway, there's this basically exponential CDF with a omega power exponent on it to get the conditional mean of the cumulative loss that people who had insurance policies through this company cost the insurance company, not counting premiums, although the premiums thing variable is in the data set as well. So this is just sort of the gross loss that the insurance company had for each person as a result of 0 or maybe more than 0 insurance claims for their car or their boat or whatever. So anyway, Gaussian likelihood, informative priors on these things, which like I said, because I can't remember what any of these mean, I can't remember why these are reasonable, but it is always reasonable to put what you know genuinely believe about these parameters before conditioning on the data and then updating your beliefs as a result of that. So condition on the data, get the estimates with respect to whatever dev is, and so it has this sort of rapidly increasing and then rapidly leveling off relationship to it, contrasted with the actual points, seems to kind of fit the observed data that we have well, even though the observed data that we have doesn't really have a lot of observations. I think this was like annualized or something. So that is actually all I have for today. Any questions? So I guess the main thing I want people to take away is that you can estimate a huge variety of regression models with BRMS without ever actually having to specify something in the Stan language yourself, and still take advantage of the nuts algorithm, the Bayesian approach in general to get like conditional probability of what you don't know given what you do know, all the tools for like base plot and glue and bridge sampling and prod spread, all that stuff that we can do with our StanR, you can basically do with BRMS as well, or at least in principle you could. I don't know if everything is totally implemented, but the ideas are all there. And so you can take advantage of all that using BRM and pretty much only have to specify our syntax. The kind of only thing that makes it a bit different is that, or not different because it's sort of the same thing in Stan, but you're sort of injecting these strings about your priors. It just copies those into the Stan code. So this with the prior business, this is the only thing where you're sort of directly writing like a little piece of Stan, just half a line. We're going to get to the point where we can write like hundreds of lines of Stan programs. But anyway, all the taking care of making the data matrix and dealing with missing values and setting it up, all that, it's handled more or less automatically or internally with the functions in BRMS. And so If you only knew BRMS, you would be way more capable than like almost anybody. Like, because, you know, Paul's more emphasis in models in psychology, and Stata is geared more toward economists. There's like not perfect overlap here, but basically BRMS can estimate pretty much as many models as Stata can. It's just not quite the same. But just literally with one R package, pretty much one function, you can estimate, you know, more models than most people who use quantitative methods would ever need. It's a little bit simpler maybe to use RCNRM for the models that are supported by that. We can go beyond BRMS to writing things, you know, ourselves in stand code, but BRMS is basically more than what almost anybody else is capable of. And you don't really have to write stand code yourself in order to use it and take advantage. So that is what has made it very popular, along with like all the things that go with it, you know, Chinese stand. Okay, so that's it for today. I will post a homework tonight about ordinal models and some stuff from before spring break. It'll be due in a week. And then next week, I'll step back a little bit from the coding and stuff, talk about matrix algebra, probability for vectors and matrices and stuff like that. And then that will be what we need to then go on to do hierarchical models. So that's what's on there. So see you Tuesday.